We continue where we left. We have finished example 6, and the conversation now switches to vertical stretches and compressions. Let us define this concept. So, having a function f, we are now looking at functions of the form a times f, where a is a non-zero constant, and functions like this will be called vertical stretches or compressions, depending on what a is. If a is greater than 1, g, which is a times f of x, will be called a stretch of f by a factor of a. If a is in between 0 and 1, g will be called a compression by a factor of 1 over a. And if a is less than 0, the graph of g is obtained from the graph of f by a combination of stretching or compression and a vertical reflection. Let me check one of the previous examples. I may have made a mistake. This is indeed a horizontal reflection. This is vertical reflection. Seems all right. All right, let's continue. So this here in blue is the graph of f. And when you put a 2 in front of f, you vertically stretch the graph of f. For example, if we have point a comma b on the graph of f, meaning b equals f of a, the point a comma twice b will be on the graph of g, because twice b equals g of a. Remember, g is twice f. And f at a is indeed b. So we get a true equality, 2b equals 2b. If you put a factor 1/2 in front of f, you can say you're stretching with a factor of 1/2, but I prefer to say compress with a factor of 2. So 0.5 times f of x is the compression of f of x with a factor 1 over 0.5, which is 2. In principle, compressions and stretches are the same thing. And for instance, if you were to put negative 2, in front of f, that would be same as first stretching by a factor of 2, and then vertically reflecting about the x-axis. Negative 2 f of x. So you stretch vertically with a factor of 2, and then to account for the minus, you flip around the x-axis. Let us now look at this example, example 7. What's given in the picture is the graph of P of t. We need to produce the graph of twice P of t. First of all, note that the domains of the two functions are the same. Domain of P is the same as the domain of twice P. And we can look at certain points on the graph of P, for instance, point 0, 1. When we stretch that, we get point 0, 2. Then the graph passes through the point 3, 2. When we stretch that by 2, we get 3, 4. We get the peak at roughly 4, a little bit over 4, and a little bit over 3, so the peak on 2p will be a little bit over 6. Note that the graph will pass through 0, because when you stretch 0 by 2, you still get 0. At 6, the value of p is 2. Stretching that by a factor of 2, we get 4. Note again that x's stay where they are. We only stretch the y's. How about this example? We have function f given by a table, and we need to produce function g of x, which is half of f of x. Well, because it's a vertical stretch, and it's a vertical stretch because we don't touch x. We multiply the function itself. All you need to do is to multiply all values of f by 1/2. It'll be a compression with a factor of 2. You can say g is a stretch of f with a factor of 1/2, which in my opinion is not very natural English-wise. I would rather say a compression of f. With a factor of 2. All right, that's it for vertical stretches and compressions. Let's talk about horizontal stretches and compressions. This time we again start with function f and consider functions of the form f of b times x. Note the difference between this and what we just did before. Before, when we looked at vertical stretches and compressions, we multiplied f by a. Now we're multiplying x by a constant inside f. As we will see in a minute, this affects the graph of f in a very clear way. If b is greater than 1, the graph will be compressed horizontally. By a factor of b. If b is between 0 and 1, the graph will be stretched horizontally by a factor of 1 over b. And if b is less than 0, you would have to perform horizontal stretches or compressions in combination with a horizontal reflection about the y-axis. Let us see at an example. Let us look at an example. The original function here is in blue, y equals x squared. Now, if we replace x by half x, where in this case it's a stretch by a factor of 1 over 1/2, which is 2. So it's a stretch by a factor of 2. Why? Why is it a stretch by a factor of 2? Well, let us imagine that this is a point on the graph, a comma b, meaning that b equals f at a. Let's use other letters, not a and b. Let's use letters u and v, meaning that f at u equals v. What do we know about this point? It has the same y-coordinate, and the coordinate of the first coordinate is bu. I claim that this point will lie on the graph of this other function. So uv is on the graph of f if and only if v at u equals v. V equals f at u. But that happens if and only if v is g at u, because g at u is all right. Let's see how to correct this argument. G of u is f at bu, and f at bu is not necessarily v. So perhaps I should take not bu but 1 over bu. Let's see if that's correct. Again, uv is on the graph of f if and only if v is f at u, which happens if and only if I think v is g at 1 over b times u. Because g of its argument is f at b times the argument. Which is true. But this happens if and only if the point 1 over b u comma v is on the graph of g. So indeed, it's a horizontal stretch with a factor of 1 over b. And you can likewise explain that say the green graph, where we replace x by 2x, is a horizontal compression with a factor of 2. I like to think about this the following way. If you think about x as being time, you may view this as slowing down of f or speeding up of f. For example, to get to value 4, f takes 2 seconds. But g will get to value 4 at time which is twice as long the time it takes f. G will get to 4 only at time 4. At the same time, the green graph will get to value 4 in 1 second. So in a way, it may be helpful if you think about it this way. The green graph is the version of f twice sped up, and the red graph is the version of f twice slowed down. I believe this is helpful. Note also that in this particular case, the green graph is simply 4x squared, and it's also a vertical stretch. By a factor of 4. But it's only in this particular case. In general, vertical stretch cannot be expressed through horizontal stretches. Let us look at an example. We have the graph of P drawn here, and we want to produce the graph of R, which is P of 2t. Again, think of R as sped up version of P, right? P, for instance, takes 3 seconds to get to value 3, right? Meaning that P at 3 equals 3. That means that R at 3/2, correct? R at 3/2, which by this formula is P at twice the argument, which is P at 3, will be 3. So R will get to value 3 in half the time it takes P to get to value 3, namely at the point 1.5. Likewise, P takes 6 seconds to get to value 2 for the second time. R will take half that time, 3 seconds. For the first time, P reaches the value 2 in 2 seconds. So R will take half that time. Now P comes to 0 after 7 seconds, so R will take half the time, 3.5 seconds. Note, by the way, that the image of both functions is the same. It's the interval 0, 3. But the domains are different. Domain of P is 0, 7, whereas the domain of R is half that interval, 0, 7 halves. So again, if you think about this in terms of speed, I think it'll make perfect sense. The red graph is the twice sped up version of the blue graph. All right, in the next example, we are working with a table. We are given the table corresponding to function f, and we need to produce the table corresponding to function f of half x. So this time we're slowing down f. In the previous example, we were speeding up f. In this example, we are speeding up f. So this new function g will be taking exactly the same values, 1, 3, 7, and 11, but at different times. For instance, it takes 2 seconds for f to get to value 1. It will take twice the time for g to get to value 1, 4 seconds. And the same with all other times. It takes 6 seconds for f to get to value 7. G will get to value 7 in twice that time. In the next example, we need to relate functions f and g when they're given by a picture. And we see immediately that one function is the other stretched or compressed, depending on how you look at it. Say we're starting with the graph of f. We see that g is the sped up version of f, namely that f gets to value 4 at time 4, but g gets to value 4 at 1/3 of that time. This, I believe, is 4/3. Likewise, f finishes at time 6, and g finishes at 1/3 of that time, at time 2. So clearly, g is f at 3x. So graph of g is a horizontal compression of the graph of f by a factor of 3. Or, alternatively, we can think of g as being our original function, and then f is the slowed down version of g. G takes 2 seconds to finish, whereas f takes 6 seconds to finish, 3 times the time it takes g. So f from here is g of 1/3 x. In other words, the graph of f is a horizontal stretch by a factor of 3. You could also say it's a horizontal compression with a factor of 1/3, but in my opinion, it is less natural than to say that f is a horizontal stretch with a factor of 3. All right, in the next video, we'll see what happens when you perform a sequence of transformations. That's it for now. Thank you.